back to our lectures. So today we will see how we can program an FPGA using Verilog HDL. Okay, so we will see FPGA design flow. So basically, our agenda is to check what is FPGA. Its architecture brief only I will take. Architecture in depth will be taken by one of my colleagues, and then we'll see FPGA design flow and a demo of FPGA flow on the remote lab later on. Okay. So this is the basic hierarchy of the things. In design methodology, we have two methods. One is full custom flow and semi-custom flow. Full custom flow is everything is custom made, even the standard cells, everything is custom made. And in semi-custom flow, we have standard cells, gate array, and programmable logic, in which you have FPGAs and PLDs. Okay, so our area is just under programmable logic. We will go with the FPGA. So this is that programmable logic is FPGA field programmable gate arrays. So in which you can program the entire gate array. I think this will be explained deeply in the architecture class. So field programmable gate array, to be specific, none of the mask layers are customized. A method for programming the basic logic cells and the interconnect. The core is a regular array of programmable logic cells that can implement combination as well as logic flip-flops. Both you can program. A matrix of programmable interconnects surrounds the basic logic cells and programmable IO cores as well. Design turnaround is a few hours. That means if you have a code of a say microcontroller or a processor, you can dump it on an FPGA and see in a few hours. You just customize it and put it on the FPGA. You can check the functionality very easily. So design flow, you should have design source files. Then you can perform behavioral simulation upon it, which we have already seen. Then you have to perform synthesis upon synthesized netlist. So before synthesis, the netlist is Verilog netlist, right? So now you have synthesized and you have made it into a gate level netlist. Now on that gate level netlist also you can perform simulation, functional simulation, verification. Indeed, it is called as functional verification as well. You can perform post synthesis simulation as well. Then you have to implement the design for the particular kit. Okay, and you can perform static timing analysis on it, back annotation if needed. That means if you have some timing issues and all, you can back annotate the design and stitch on the design and come back from the synthesis step, and then you finally generate a bit stream and then upload onto FPGA board, and in circuit verification that you can see it on the circuit. Either you give physical inputs like switches and LEDs as outputs, or else you can see using some tools called chip scope, virtual input, virtual output. They are all IP cores in in logic IP cores or hardware IP cores, which can be plugged into our design and can be seen from the remote place. So we will see all those things. So basic elements of FPGA, I'll just cover that. It is configurable logic blocks, and then you have something called configurable IO blocks, IOBs. Two-layer metal network of vertical and horizontal lines for interconnecting the CLBs and IOBs. That they are called as programmable interconnects, as you can see clearly in the picture. So this image you should have in mind whenever FPGA comes into picture, and it will be having a small configuration memory to which we will download our bitstream, and then that bitstream will contain only ones and zeros. That ones and zeros will configure the logic inside this particular circuit. Now this is what it is meant. The detailed view you can see here, CLBs, then switch is there, which can route the wiring. Okay, an LUT and how LUT can be configured, this will be taken in depth by my colleague, but I'll just show. A lookup table or LUT, which stands for lookup table, is basically it's table. It's a table that determines what output is for a given input. So that for a combination circuit, it is two table. So if you take this particular combination logic function, you can see A, B, C are given here, inputs, and output is given here. So if we give A, B, C as the input of the mux, and you connect all of the input of the mux to the SRAM, wherein which you can input all this output into the SRAM cells. So if ABC is 0, 0, zeroth line will be selected to the output. That means 0 will come from here. Okay. And if it is 1, 1, 1, it should be 1. So I will store a 1 in the 7th line of the or 8th line of the mux. That's very simple. Okay. So this is what a lookup table is basically used in FPGA. So say combination CLBs are also given here. CLB required. So if you want to get interconnect two CLBs together, this is the algorithm which is used inside the FPGA to configure that CLB1 and CLB2, and how CLB1 and CLB2s are connected. What are the configuration bits required for this? So these are the configuration bits which comes into this SRAM and to this mux select line. So that can be easily determined. So you have a lot of ones and zeros which is put into the configuration memory like this, and then finally it will come into as a circuit. So if you want to read more on this, a highly flexible reconfiguration system on Xilinx FPGA by Thomas is there and Martin is there in 2014 reconfigure conference. You can read that. So this is what the basic design flow look like. Now it has a design entry on either in HDL, then you perform a behavioral simulation. If it is not okay, you again tweak your Verilog design and make it correct. Once behavioral simulation is correct, then you should put some constraints. What do you mean by constraints? Suppose I am having a kit called RTA7 FPGA, and I am going to synthesize a full adder. So full adder has three inputs, A input, B input, and a C input, and output carry and sum. So I want to give this three input to my switches. So my constraints here is these switches. I want to connect my A to one switch, B to one switch, and C to one switch, and sum to one LED and carry to one LED. So that this is the basic constraint structure in this particular program. Now if you go to a bigger program in which I have a clock, so I have to define the clock, where I have to connect the clock, what is the frequency of the clock, everything I have to mention in my constraints. So after giving the constraint, you go ahead with synthesis. What synthesis does is it combines this constraint file and the design which is written in Verilog into a gate level netlist. So it will be a ngc file. So after that we perform a translate, okay, that is called as ngc build, and now you get a ngd file. After that you have to map that file. Everything is automated process, but you should understand the steps. Mapping is done, then you get a mapped ngc file, then you have to place and route it functionally, and then you get a routed ngc file. At each of these steps you can perform functional simulation and check whether it is okay. If it is okay, you proceed to next step. Otherwise you can modify the design, change the design constraints, or modify the settings from the previous steps, or all you can tweak. Then after this place and route you can perform static timing analysis, and you should analyze the timing report so that you meet the slacks properly, and then you generate the bit stream. Then you can do the device programming once the bit stream is generated onto the FPGA device. This is what we are going to do in a couple of days in the FPGA lab. Okay. So design specification, what are the main design considerations? Design feasibility, its performance, power consumption, cost, chip area. If chip area matters for your target board, that so because everywhere whenever we do an FPGA emulation, finally the target will be an ASIC. So if you have a chip area constraint on that, you have to take that also into consideration when you emulate it on an FPGA and C. You design specification, oral or written document will be there, and you can convert that into system Verilog or VHDL or C++, and then you select the implementation platform, either it is an FPGA or CPLD or ASIC, which FPGA, which CPLD, which device family, what is the development time, all you have to fix whenever you go with the design specification. So functional simulation, we have already seen functional simulation in Vivado, in Icarus, and in Cadence Iron. If possible, I will show in Model Sim as well. Model Sim is a pretty easy tool, so you can Google it and find out how you can do the simulations, generate waveform patterns, and generate the simulation netlist and see how the design is working. So it's very fast, but you need very good skills in creating very good test benches. So what is synthesis basically? FPGA synthesis, as suggested by name, is the process of converting high level FPGA logic design into gates. So if you write assign y is equal to a and b, or y is equal to a and b in this is in VH, this is in Verilog and this is in VHDL. So what is happening here? Verilog or VHDL code synthesis ngC file is created. Now from this writing I have to get this gate. That is what. So synthesis is nothing but translation plus optimization. Translate HDL design files into gate level netlist. Optimize the design according to the area constraints, timing constraints, and power constraints. What are the main challenges? Learn synthesizable coding style Verilog and VHDL. There are a lot of unsynthesizable constraints in Verilog and VHDL which you should never use if you want to go and synthesize the design. Learn how to write good design constraints. So you have to write the appropriate constraints for power, for timing, for area, etc. Use HDL synthesis tool effectively, and or Xilinx, Vivado, or Intel's Quartus 2 or any equivalent tool for using it very effectively. These are the main challenges. So some reports after synthesis, you will get some utilization reports which actually shows us number of slices is used only to available is something like this, percentage is 0 because it's very small if we have used. Number of slice flip-flops used is 4. You have 9,000 of them, but okay. Like this you will get a synthesis report, and it will also show 2.25 nanosecond is the maximum frequency achieved is 500 megahertz. So, so what is the slack? Everything is mentioned in this. After synthesis, you get these kind of reports. Now, implementation. What do you mean by implementation? Now, you have a gate with you. Now, you want to put it into ones and zeros and put it on an FPGA chip. That is what implementation does for you. So, netlist merging, flattening, database building, design rule checking, whether it's as per design rule, logic optimization, block mapping and placement, net routing. So I want all of you to read on all these things. I'm not going to elaborate on this because my intention is to make you learn how you can convert a Verilog design into FPGA through using Vivado tool. So I will be focusing on the demo part of it. You can very well go and search for all these lines of I have put on my slide and try to understand more on it. If you have very specific doubts, we will clear that in a live sessions possible. And configuration of bitstream for FPGA implementation results. Check for design errors, warning, FPGA utilization reports, timing reports. Challenge is how to reach high performance and high utilization in implementation. So you have to write particular synthesis constraint commands to achieve this particular thing. So we'll learn all those things. Implementation steps. This process consists of a sequence of 3 steps: translate, map, and place and route. Translate process combines all input netlist and constraints to a single logic design file. This information is saved as an NGD file, native generic database file. This can be done using NGD build program. Here, defining constraints is nothing but assigning ports in the design to physical elements such as pins and switch and buttons. That is, I have already told you, of the targeted device, and specifying the timing requirement of the design. This information is basically stored in a file called XDC file, which is also called as Xilinx design constraints. Mapping. Map process divides a whole circuit into logical elements into sub blocks such that they can be fit onto FPGA logic blocks. That means map process fits the logic defined by the NGD file into a targeted FPGA elements combination of CLBs and the IOBs. So NGC file is the input to the translate step, and you perform a algorithm called NGD build, and NGD file will be generated, which can be utilized for simulation, function simulation. Here NGD file will be given to the mapping, FPGA mapping algorithm, and you get a NCD file. You can perform static timing analysis on this NCD file after the mapping stage. So now, place and route. PAR is a process PAR program or PAR algorithms are used in this process. That is nothing but place and route. The place and route process places the sub blocks from the map process into the logic blocks according to the constraints and connect them in the logic blocks. Okay, so it consider lot of constraints, which are if you have a clock frequency and if you have nearby blocks, all those things will be considered into account. So the trade-off between all constraints and the place and route process. So here the constraints become very important. So Vivado takes the mapped NCD file and FPGA mapping and the place and route is done and routed NCD file will be generated. So now after that you have another program called BitGen program. You run that. Now the design can be loaded onto the FPGA file after this. A .bit file will be generated, but the design must be converted to a format so that FPGA can accept it. BitGen programs deals with this conversion. Routed NCD file, that is from the place and map stage, is given to the BitGen program to generate a bitstream .bit file that can be used to configure the target FPGA device, which can be done using a cable. So that I will show you a demo in the next lecture.